There's a way to rewrite this as an operator notation. This is second derivative, so if I say d is the derivative, you can rewrite this as d squared applied to y. And you can think of y as 1 times y. And you can rewrite this as d squared plus 1 times y equals to 0 by factoring the y out. Okay? And here the important thing is d squared plus 1 is a linear operator. Now, what this means is that if you have d squared plus 1 applied to two functions, f of x and g of x, well, you can basically apply this separately. So it'll be d squared plus 1 applied to f plus d squared plus 1 applied to g. Is this okay, or do you want me to verify? Is okay, or do you want me to verify? It's pretty true, right? All I'm doing is take the second derivative of this, add to itself, and it will be the same as doing this separately. And then it's also true that d squared plus 1 applied to some constant times function is same as constant times d squared plus 1 applied to f of x. So these two are the conditions a linear operator must satisfy.
I have a question.
Yeah.
In differential equations, when you're like trying to find like duplicates, does that also go in?
Oh yeah, we had duplicates. So that was, yeah. But if we start talking about duplicates, then it'll be a full-blown differential equations class. So, but you know that's a good thing. No, let's not go there. Yeah, but okay. So coming back. So what it means is that the solution space, so what this implies is that solution space is a vector space. Ooh, okay. What's a vector space again? What's the abstract vector space? There are 8 conditions, right? Well, you need what? You need 2 operations. What are those? Oh, come on. What do you need in order to say it's a vector space? You should be able to do what?
Vector addition?
Yeah, you can. You should be able to do vector addition, right?
Multiplication.
What multiplication? It's called scalar multiplication, right? If you can do scalar multiplication and vector addition, then it's a vector space. But look, if I considered solutions of this differential equation, right, as vectors, like just these are abstract vectors, okay? Then adding 2 solutions will be again a solution. So let's see why. If d squared plus 1 applied to f of x is 0, and d squared plus 1 of gx is 0, so that these both belong to solution space. Solution space, let's call this V. Okay? So they both belong to the V. Right? Then what is d squared plus 1 of fx plus g of x? Well, this hitting this will give you 0. This hitting this will give you 0. So what do you get? You get 0 again, right? So that means this, again, belongs to the vector space. That means taking 2 solutions, adding them again, is in the it's in the space, so vector addition is defined. It's a simple addition of functions that can be taken as a vector addition. Right? Also, you can take any multiple of a solution, right? And then what? You can bring the C outside, and therefore, when this hits this, you get 0. Okay? So any multiple of a solution is again a solution. And that has to do with the fact that this differential equation is a linear homogeneous differential equation. If the right side is non-zero, then the solution space is not a vector space. Okay? It's only because it's a 0 that its solution space is a vector space. Okay. Then, the obvious question that you would ask next would be like, oh, okay, so how big is this space? And the way we measure the size of a vector space is the dimension. We talked about one-dimensional vector space, two-dimensional, three-dimensional, stuff like that, right? Guess what the dimension of this vector space is? What's the dimension of this vector space? What do you think? It's two-dimensional because it's the second order differential equation. Actually, we know the basis for this vector space. I mean, we didn't define what a basis is yet, but I'm trying to use this as an important motivation of why we would want to use a basis. See, the way we solve this in differential equations, if you forgot, we first write down the characteristic equation, right? R squared plus 1 equal to 0. Solve this, R squared is -1, so R must be plus minus I, right? If you have plus minus I, what's the solution? Y is?
Cosine of x plus I sine x?
Yeah, cosine and sine x, right? It should be C1 cosine x plus C2 sine x. Right? Yeah. See, one of the things that you should try to do is like help your friends out who is taking differential equations. It's really helpful for your own good. Yeah. If somebody's doing homework for Calc 3 or differential equations, just say that, hey, I like this. Can I help you? And try it out. It works. Okay, so that's what it is. Now, let's look at this statement. What does it say? It means that any solution of this is a linear combination of these two functions. Okay? Now, first of all, let's check that this and these two are solutions themselves. Okay, so what is cosine x double prime? Well, that's like negative sine x prime, right? So it's negative cosine x. So if you have cosine x double prime plus cosine x, is going to give you negative cosine x plus cosine x, which is 0. So this, indeed, when you plug in on the left side, you get 0. It's a solution. You can do the same thing for sine. If you differentiate sine twice, it's negative sine, so if you plug them in, you get 0. Right? So that tells you that these themselves belong to this vector space of solutions, and any other solution is a linear combination of these two. Moreover, we know that these two are linearly independent. It's not a redundant list. You can't just survive with one of them. You need both. So, how do we know that? Well, suppose C1 cosine x plus C2 sine x is 0, right? So maybe I should write this as a formal question. Show that cosine x sine x is, this list is linearly independent. Okay. So how do you show it? Proof. Suppose this is true, and we end up showing linear independence if we can force C1 to be 0 and C2 to be 0, right? So we just plug in x equals to 0 there. Then, see, this is an equation among functions, so it should be true for any value of x, right? So if you plug in 0, you get C1 cosine 0. What C1 cosine 0 is? 1. Sine 0 is? 0. So you get C1 equals to 0 right away. Then we plug in x equals to pi over 2. Cosine pi over 2 is?
0.
Sine pi over 2 is? 1. So this time you get C1 is 0. Now you proved that both C1 and C2 has to be 0 for this to work, so you're done. You've shown that these two are linearly independent. Okay, now another proof. In differential equations, you showed this using something called a Wronskian. Do you remember Wronskian? Okay. The problem is, if I have cosine x and sine x, we can't take the determinant because it's not a square matrix. But there's if these are functions, there's a nice way to make a determinant out of it. How?
Oh, isn't it with like the e? I forgot.
No. You just differentiate.
Oh, right.
So if you have 3 of them, you have to differentiate twice to get a 3 by 3. So whatever you do, you make this work, and then you take the determinant. And then if you can show that that's non-zero, then it can't be linearly independent. It can't be linearly dependent. It's linearly independent. So you multiply this minus that, so what's that? Cosine squared x minus negative sine squared. Oh, but that's cosine squared plus sine squared. What's that? 1. Right? Sine squared plus cosine squared is 1. Done. Is that okay?
Yeah.
So
if it doesn't equal 0, it's linearly
independent.
independent.
Yeah. If it's equal to 0, it's linearly dependent. Okay? Now let me conclude this part. I wish I could devote more time to this, but then if I do, then this will be just differential equations class, which we all took. I'm just trying to give you a new perspective because we're doing vector spaces, and actually the differential equations that we've learned has a lot to do with linear algebra. That's why some schools, when they teach differential equations, they make it differential equations with linear algebra, and they take a lot of stuff out, but then fill everything with these linear algebra. That's one approach. Okay, but anyways.
Is the way you teach it like a unique way, or?
No, here in Maritime we do it a little unique way because we are a little light on math load.
Really?
Yeah, we teach less math in an engineering curriculum compared to other schools. We have more hands-on stuff like machining and stuff like that. So that's a trade-off. We always take pride in having hands-on classes, right? But because of that, we have to expose people to partial differential equations. So our differential equation class takes some portion of the class devoted to partial differential equations, which makes our linear algebra part to be real light.
So you take differentials as a prerequisite class?
No, I'm. So it's like it's best if you learn it together.
Oh.
I think.
So,
But then again, it's like it takes several takes. Like you want to review linear algebra and then go back to differential equations, see, and then everything makes sense in a different way.
so other schools have like a partial differential, a partial.
They have a separate PDE course.
Okay.
So some of your mechanical engineers, who's going after a PE degree eventually? Okay. PE, yeah.
Like the license?
Yeah, PE license, yeah. Oh, yeah, okay, yeah. Oh, several, okay. So you guys, when you take the PE exam, there's a portion that has PDE in it. Yeah. but they only have easy ones. I think we covered most of it in our differential equations class.
That's for all, degrees, like EE, mechanical, or is that one?
I thought PE was only for mechanical. Does EE have PE as well?
Yeah.
Oh, I didn't know.
Yeah.
So E and ME both have PE, okay.
And civil.
Yeah, they all have.
Civil.
Yeah, everyone has them, yeah.
Yeah, but I think all of the PE exams have the math portion, and one of them is linear algebra, and one portion is PDEs. It would be nice if we can cover both, but we don't have it. Yes.
So we won't have PD in the FE, partial differential equation in the FE, or rather the PE.
Yeah, I think it's a PE exam, not the FE exam. The math portion I only saw I just happened to stumble upon an old copy of a PE exam, very old, so maybe they changed, but I shuffled through it and there it was, PD heat equation, which we solved using separation theory. Okay, so going back, let me add a little bit more to this. Look at the following function: f of x equals to e to the ix. Okay. Oh, let's just say this is y. Okay, what's y prime? I times e to the ix. Okay, what's I double prime? I squared e to the ix, but I squared is negative 1, so you have negative e to the ix. Oh, so what's y double prime plus y?
0.
0. Oh, what does that mean?
It's linear independent.
No. This, if I take the second derivative and plug it in here, I get 0. What does that mean?
It's the C1 cosine x plus the C2 sin x.
Okay. All right, so that's one way to say it. All I wanted to say is that this is a solution to this.
Oh.
Is that okay? Now, the only trouble here is that because this is a complex valued function, now some of you might be a little worried that there's an imaginary number up there, but that's okay because we can take exponential of anything, right? It's always the Taylor series, right? It's 1 plus ix plus 1 over 2 factorial ix squared plus 1 over 3 factorial ix cubed, so on and so on, right? Yeah. So if you plug in some real numbers, you'll see that this produces not just the real number values, but also imaginary values. So the output will be a complex number. So in order to include this as a solution to this, you have to expand this vector space as a, I raised it, but the vector space should be a vector space over C, not vector space over R, okay? So let's say we have a vector space over C, and now we have a new element, right? And then the question is, okay, so what do we do? So we have two options. One of these two things will be true. Maybe this system, cosine x, sine x, e to the ix, they form a linearly independent list. So that now the solution has to be written as y equals to c1 plus c2 times c3, just like that. That's one possibility. Another one is maybe this is redundant. Maybe it's linearly dependent list, which means one of them should be linear combination of the other, which means that this should actually be e to the ix should be something times cosine x plus something times sine x, right? So either one of these two would be true. If it's independent, this is what we have. If it's dependent, this is what we have. You got that so far? Okay. And I want to say that this is an important consideration if you're really trying to find all the solution of this, right? I mean, if you want to find all the solution of this, it's important to know if this is the general solution or this is the general solution, right? Yeah. So linear independence in this context is a very important thing. All right. So which is right?
p to the ix is equal to.
This last one, yeah, this is right, okay? This is not linearly independent. This is dependent on the other two, okay? All right, so how do you know?
I mean, that's the Euler identity.
Yeah.
Oh.
Oh, that's wonderful. Okay, so that's one way to say it, the Euler identity. But before that, we can also do the Wronskian. We can do cosine x, sine x, e to the ix, and then to make a square matrix, you differentiate twice, differentiate once, differentiate, and then twice, and then differentiate once, twice, and then you take the determinant, okay? Now this is a very long calculation, so I don't want to do it, but if you do it, guess what you get? You get 0. Okay. So that means there's some kind of a linear relationship between these three functions. Okay. In other words, you should be able to write this as a linear combination of these two. What is it? As Nicholas said, it's the Euler identity. Okay, so what is the Euler identity? E to the ix is same as cosine x plus I times sine x. Okay. How do we know that this is true? Well, just write this out. If you expand this out, then you can collect the real part and the imaginary part. If you look at the real part, it's really the Taylor series of the cosine function, and I times the Taylor series of the sine function. So that's true. Okay. So that's how you can know that this is actually true. So hopefully this example could kind of motivate you in thinking about why we would want an abstract vector space and still talk about linear independence, span, and all that, right? Okay. So when we say this is true, here's what we're saying. We're saying every solution in here is a vector in some abstract vector space, and it's spanned by these two vectors, cosine and sine. Right? And these two vectors also happen to be linearly independent, which says another thing. It means that the expression is unique. So that's like one part that I should do.